All right, so let's get started. We have a lot of material to cover. Are there any questions from the last few lectures? All right. Nobody ever asked questions of the last few lectures. Turn up the volume. Okay, I can do that. How about now? Is that better? Okay, that's fine. So if you remember where we left off, I was talking about sexual selection. I want to finish up that lecture. I want to get to species concepts. And so the idea will be, in terms of plan of action, sexual selection. Finish up that. I want to talk about species concepts. I expect I'll be able to get through both of those topics in this lecture. And then after the next lecture on Monday will be speciation. How do new species form? Okay. So let's just go ahead and finish up this lecture. So I was talking about an example of good genes. That is to say, in the case of mate choice, female mate choice, for what reasons might she choose a particular mate? I went through direct benefits. That is to say, the male, for instance, brings something that will directly benefit the female, such as food or a good territory that has lots of food in it. That would be examples of a direct benefit the female will get by choosing a particular mate. Indirect benefits are a little more difficult to quantify, but they would be reasons such as if you mate with a certain individual, your offspring will have obviously you have the genes from that individual. So if your offspring have the good genes that in your mate, maybe those individuals your offspring will survive better or have more offspring. Okay? That's the idea. And so this particular example, in that idea works on several things being true. Several things have to be true, such as there has to be variability in the quality of the mates you're choosing. Right? Some of them have to be good, some of them have to be bad. There has to be differences in the advertisement the males have. Right? You have to have something that you're choosing. And so an example that people that's been worked out pretty well is when I was describing at the very end of the last lecture involves female frogs that choose males that have a long call versus a short call. Okay, this particular example, if the female chose the long call males, there were several measurable differences in the offspring she had that were associated with the long call, and here they are. Where we see at LC, you have a statistically significant difference between the long call and the short call males. We've actually finished that up. So the final topics I want to talk about with sexual selection involve lekking, what is a lek, and the evolution of leks, and the sensory bias exploitation hypothesis. So let me tell you what leks are. They're pretty common in birds. They're basically an area where males aggregate, and the only reason they're there is they're aggregating in a particular place, and they're just there for mating. As I say, the females visit these lek areas, they shop around, and they choose a male, and they mate, right, and then they leave. Okay, so it's just an area where the males are aggregating just for the purpose of mating. These are cases where the male isn't being particularly parental. They're not there because the males are going to be helping her raise offspring. The only contribution the males have is their sperm. We went through the second option here, the second point. And the display sites that the males, these lekking sites may or may not be places where the females are feeding. They could be there because they're feeding and they're visiting males, or there may be no other reason why the females are visiting these areas. But the main point is that the females are there, they can shop around. That's the main point. I think I'll skip this part a little bit and just give you a good example of a lek. A really good example of leks are bowerbirds. Okay, they live in places such as Papua New Guinea. This is an example of a male bowerbird. They have these beautiful satiny feathers. And it's hard to see, but you can see that there's this grass, and he sort of trampled it down into the shape of a U. That is the bower. Okay, this is the courtship arena, so to speak. And you can also see that this male is dragging all this blue stuff. Right? In the past, it would have been things like blue petals or anything that you could find that was blue in nature. But these days, bottle caps are great. Right? So they'll actually bring in bottle caps. Anything that's blue in this species of bowerbird, at least they'll bring in. And here's an example of a bowerbird. The female is visiting this male's bower, checking it out. It's nice work on the leaves. The male's doing a little bit of a dance, saying, "You like my bower? How about me?" And she's checking it out. So this is nice, and then we don't know what happens. I know. Wish the video were just a little longer. He went out or not, although maybe we don't actually see what would happen. But the important point is that in this area of the forest, this is not the only bower. She could go 5 meters away and find another male with another bower. Right? Maybe his bower is better in some way that the females prefer. Okay? So that is an example of a bowerbird. This is a lek. This is his little bower that he made to impress girls. In terms of how these leks might evolve, there's a lot of different models. They're difficult to test, but I'll at least point out some of the ideas that are out there. One idea is that in these areas where these lekking sites, for some reasons, for whatever reasons, they're areas of lower predation. So the males can hang out there and the females can visit there without as much risk of predation. So this would just have to be, for whatever reasons, there's fewer predators in that area. Whatever that reason might be, that's why they chose it. There could be an idea that, or another idea is that the more males you have in an area, it's kind of like the idea behind shopping malls, frankly, right? The idea that if you have a lot of shops congregate in one area and make it convenient, right? You park your car once, you go from one little store to the next, you do all your shopping, and you leave. Well, one idea is the same, that these leks might evolve because sort of a convenience factor for the females. You have a lot of males in one area, and that drags in more and more females who want to shop around for the males in these areas. It could be that there's a bunch of males that are congregating around a really good male, right? So this is the so-called hot shot model, or the hot spot rather. The hot spot model is one rather. I actually can't see my own slides. The hot shot model is the very last one. The females are always choosing the best male, but the males aren't quite as good, or congregating around a very good male in the hopes that maybe some female will become confused, I suppose. That's the hot shot model. The hot spot model is that these areas, for whatever reasons, have a lot of traffic. So this is sort of the choose the off-ramp sort of approach to lekking sites, right? You want to make certain it's an area where there's a lot of traffic coming through for choosing these lek sites. And then there's finally this black hole model that the females aren't really choosy, but they wish to avoid dangers associated with mating. Okay, so that's a bower. This is an example. This is a lekking species, these bowerbirds. There's many different types of bowerbirds. Each species, different species of bowerbirds. Different species have different sort of bowers. So here's a kind of maypole type of bower. The male runs around, or the female kind of checks out this little area and is impressed. And I'm kind of actually impressed by that one. But just give you an idea of the variety of, yeah, not that way, but I am impressed. But yeah, just give you an idea of the variety of bowers in these different bowerbird species. And the final thing, I just want to show you these two slides, so I can't help it, right? So there's a number of evolutionary biologists who study bowerbirds. If you're interested in sexual selection, sometimes you try to pick species that you think, the terminology used, I chose the particular species because it's a good model for sexual selection, for instance. So a lot of people think bowerbirds are especially interesting because they seem to be manipulable, and there's lots of interesting questions you can address with bowerbird species in a pretty easy way. And you get to travel to some pretty cool places. There's this one fellow and a graduate student live in Maryland, University of Maryland, who studied bowerbirds, and they were actually interested in the cues that the females were sending to the males about whether they should really like it or not. So what they ended up doing, they weren't not responsible for this slide or the next one, but I thought it'd be fun to show you. What they ended up doing is making robotic female bowerbirds. Imagine doing that for your graduate work. And this is an example of one of these female robot bowerbirds. Of course, you can imagine it was almost irresistible, but you had to call them fembots. So they made their little bowerbird fembots. And this is what while the male was off getting some food, getting a quick snack, they'd sneakily come in and plant one of these robotic females in a bower, and they'd hide out in the bushes. I imagine mostly giggle, but also perform their experiments. And I just have to show you this one. So here's an example of what's happening. Here's a robotic female, and she's sending off signals from the person behind the bush remotely, and the male's trying to decide, how do you like me? And she's evidently they're sending the signal, I really, really like you. And this is so pathetic. This is one of the saddest things I've ever seen. So I don't know if she's really cold and unfeeling or whatever, but this was just a really, yeah. So I just wanted to, all right, so now we're back. So that was just a short digression. We're back into the serious land. Now we're, not that that's not serious, but now we're going to go back to our regularly scheduled programming, so to speak. And I want to talk about one last idea. And this is a fairly easily testable idea. It's a so-called sensory bias exploitation hypothesis for the evolution of male traits, male exaggerated traits. And the idea is that, like anything else in any other trait, your senses can also evolve. So, for instance, your sensitivity to different wavelengths of light, or your hearing, especially, we have very good hearing, but some organisms like frogs, they have hearing that's very tuned for some frequencies, but not for others. Right? So you imagine that the tuning for your hearing can actually change from one species to the next. So we do have evolution for whatever reasons of our senses, undoubtedly driven by natural selection. So whatever the reason is for the evolution of these, the changes in the senses that these species have, the idea is the male traits evolve to exploit them. Right? So the idea is you have evolution, for example, of in that species for hearing at a different frequency. And so the male's trait then evolves to exploit that, that new frequency. And so here's a nice example. This was an example that was published in a very prestigious journal about 20 years ago. It was this graduate student who was in a different lab than my, the laboratory I was in as a graduate student, but Alexis Basolo. And what she did is she studied platyfish. And if you look at platyfish, the males in many species have these so-called swords. If you look at the little projection off the tail, right, that is the sword of a sword-tailed fish. And the ancestors of these platyfish, these sword-tailed fish, do not have these swords. So the platyfish is the one on the left. Note that the males don't have a sword on the tail there. Okay. So the idea is she wanted to, so she noticed, or people have noticed for a long time, that some species have, sword-tails have these swords, and the close relatives don't. You can actually map onto a phylogenetic tree where the swords actually evolve in these species. Right, so you can see the males have the swords here, they don't elsewhere. So our hypothesis would be that, or our best hypothesis, that the swords evolved along this branch of the tree. That's the easy part of her study. It's like, do you have a sword or not? That was just a simple, what they call phylogenetic analysis, plotting onto the tree where the swords evolved and where they didn't. Okay? What was more difficult is to determine whether the females actually preferred males with the sword or not. Right, so what she did experiments in the laboratory on females with, which normally mate with males with swords. And she did the simple manipulations you might expect. She would do things such as artificially lengthen or shorten the swords in the males and ask whether the females had preferences for fish with longer or shorter tails than normal. Right, so take a fish with a sword already, you lop off the sword, and you artificially then put on a sword the same length, shorter or longer. So the idea is when you lop off the tail and you put on a new tail, artificial tail the same length, that's your control. Right? And what you found is that the females always preferred males with longer swords, even longer swords than normal, that you normally find in the species. Right? So yes, you'd find that the species with swords, where the males already have swords, the females really do like the swords. And if you have a short sword, they don't like it. Right? So that's an example of, yes, we know the females have a preference for the swords in the species that have the swords. But how about in these species that don't have the swords normally? Would the females prefer a male that has a sword, even though normally there's no swords in those species? And so she took the close relatives of these sword-tailed fish, and she did the same experiments. This time, of course, she didn't have to lop off a sword, but she could then artificially put on swords of varying lengths. Okay? And she found the females like the males with swords, even though the species doesn't normally have one. And the longer the sword, the better. Okay? So she was able then to say, all these species here, the females actually prefer the sword. So the preference in the females, for whatever reason, evolved before the male trait actually did. Right? And this pattern is consistent with the sensory exploitation hypothesis. Okay? That's to say that if you have the male's trait responding to a pre-existing sensory bias in the females, then it has to be the case that the male trait evolves after the female preference. This is an example of that. Okay. That is all I wanted to say about sexual selection. I'm trying to find the lights so I can bring up the lights. Oh, or somebody can just do it for me. Thanks. So that's it for sexual selection. Are there any questions, by the way, before we move on? Yeah, go ahead. They're different species, yeah, and I simplified that a lot. So she didn't just do the experiment in 2 species. There are a large number of species. So I simplified it here. The phylogenetic tree with 2 species is really boring. Okay, that's a good question, though. Okay, so I want to go on to species. We've talked a lot about species kind of very loosely. I've told you, for instance, that every species is composed of at least one population, right? And we describe what populations are. But we haven't really discussed what a species is in nature. And it's important, too, because if you think about Darwin's great book, it was on the origin of species, right? And it's remarkable that we talk about natural selection. He described a lot about natural selection in the book. That was his main mechanism. It's remarkable. He didn't really talk a lot about how species are actually formed. But it turns out that species formation is one of the hottest topics now in evolutionary biology. A lot has been learned about the details of how species formed in just the last 10 or 15 years. And I'll try to describe some of that research in the next lecture. But before we really go there, I think it's worthwhile considering what is a species, what are some of the practical difficulties that you would sometimes encounter when you try to identify or describe species. I should say that in most cases, identifying species is pretty easy, right? Distinguishing a dog from a cat, that's not too difficult. But there are cases, especially when 2 species are very closely related, that it becomes more difficult, right? So there are practical problems involved. But kind of historically, species were described based on the traits that you could observe. This is the so-called morphological species concept. Or the MSC. Right? Morphological species concept. You're going to distinguish species based on what you can actually see in the traits. And so what I'm going to do is just make this pretty simple. I'm going to imagine we have 2 traits we're going to look at, trait 1, and we'll have trait 2 over here. These traits could be anything you can imagine. It could be length of certain features, whatever. It could be weight. It could be maybe some measure of color, whatever you want. And one thing we do not really observe and have problems with is a situation like this where you actually have 2 species that are very difficult to distinguish morphologically, where you have to sort of make an arbitrary cut between the 2. That is not something we normally see. What normally happens, what we normally observe, I'll be right back. What we normally observe is patterns like this, that in nature, if you were to do this experiment where we actually measure different traits, you find individuals cluster in the observable traits that you can measure. Okay? This is the pattern we normally see. It's almost a universal pattern. And what people will do then is they say, well, this group of individuals is one species. They might distinguish, say, okay, these individuals are all clustering together morphologically, as to say they look similar one to the other, or one species. And this other group of individuals that all look very similar one to the other are another species. Okay? That is the morphological species concept. Okay? Now, you still have to decide on a name. So if you're a virologist, really you don't have that much to work on except for maybe some genetics. You might call that Phi-X174, which is a really lame name, right? But that's the example I gave earlier of the DNA phage that Jim and Holly worked on, Professors Poole and Rickman worked on. That was how virologists often name things. But that's the exception, not the rule. Most people, the agreed upon standard among biologists is to name species according to the Latin binomial system that was described or devised by Linnaeus, who was a Swedish scientist in the 1700s. So we're going to use the Latin binomial system. It was devised by Linnaeus. It's called sometimes Linnaeus is a very, the Swedes, he worked at University of Uppsala in Sweden. When I was visiting there, they very proudly showed me the place where Linnaeus lived. He's on their money. The place is on their money. He says the Swedes are very proud of him, rightly so. He's a great biologist. And this Latin binomial system, the idea is that every species has two Latin names associated with it. One name is called the genus, and the other is the species. That is the binomial part of this, two-name binomial. And they're in Latin. Okay? As an example, Homo sapiens, that is our genus and species name. This Latin binomial system actually developed from an earlier system where, in the old days, all scientists, all scholars really had no Latin. It was like the language everybody communicated in. Of course, it's a dead language for the most part, except for at least in the 400 years ago, scientists used it. And so the original system was to have a short Latin descriptive phrase associated with species. And so Linnaeus just took that system and sort of formalized it a bit, right? So let's have a genus and species name. Just as an aside, these are types of things actually they don't drive me nuts, but I find a little annoying. The genus name is always capitalized, even if it doesn't start a sentence. All right? And the species name is always lowercase, except in the very unusual case where you might start the sentence with sapiens. I don't understand why you ever do that, but if you want to write a crazy sentence like that, I guess you would make capital S. And also, these days, they're supposed to be italicized, just like a ship name should be. And if you don't have access to italics, or you can't write in chalk and italics, then underline the name is supposed to indicate italics. Okay? That's just some of the ways you actually see it written. So if in the newspaper you see Homo and then with the capital Sapiens, you'll just realize that the editor never took a biology course. Okay? Not that that's a big deal, but just some people get very worked up about these things. All right, so and just one other point I want to make is that the genus species name is part of the Linnaean hierarchy. So every species is not only assigned a Latin binomial, the genus and species name, but they find themselves in a hierarchy of other names. Right? So we will talk about the Linnaean system when we talk about trees or classification briefly, and I'll give you a good way of remembering the system. But for right now, just realize that every species has a genus and a species name associated with it. So that is the morphological species concept. It's a great system for many species. It's one that actually is pretty useful in most cases. And historically, this is the system that was used. But there are some problems associated with it, or some difficulties. I'm not saying that this doesn't mean you can't use them, but there are certain circumstances where it's very difficult to apply the morphological species concept. And now this is one example. So these are my favorite organisms. Now, you guys probably know by now that I'm a theoretician, but the only work that I'm currently doing on anything that's actually alive involves this group. They're an order. So once I didn't say you had anything yet, at least about the name hierarchy, but they're an order of insects. This is Strepsiptera, an order of insects. And so they are of the same level in the Linnaean hierarchy as things like beetles or diptera, those are flies and so forth. They're the same level, but they're hardly known by anybody. They're very poorly studied. Even professional entomologists rarely see these critters. Right? And the reason why is they have this crazy life cycle. So this is they're wholly parasitic. They parasitize other insects. So what you see on the top left is a wasp, an unfortunate wasp. So it's been parasitized by a Strepsipteran. Now, how many people have seen the original Alien movie? All right, so many people here will know what I'm saying. If you haven't seen that, it's a good movie. So it's still, I think, one of the scariest movies I've ever seen. It's a good one. But there's a scene in this movie which, I hate to spoil it, but the best scene in this movie is when this guy's recovering from this incident, and they're eating food, and this monster comes exploding out of the stomach. It's a great scene. It's very memorable. Well, this is a similar situation, right? So what happens is that the female parasitizes the wasp. The female takes up the entire abdominal cavity and extrudes offspring. It's just like a little baby-making machine. That's all she does. Is it extrudes offspring. And so you can see where the arrows are pointing is where part of the female is poking out of the wasp. It's really gruesome. But the interesting thing is, as she's extruding offspring, unlike in the movie Alien, the host doesn't die immediately, but it can't be pleasant, I'm sure. But anyways, that's the female. The females look like undifferentiated bags. I mean, they're very difficult to even recognize unless you're a professional entomologist who studies the group as insects. This, on the other hand, is a male Strepsipteran. That looks like an insect to me, right? It has legs, it has antennae, it has eyes, it flies around. The interesting thing is these males, they'll emerge from the female, and the clock starts. They only live for a couple hours. The males actually don't have functioning mouth parts or digestive system, which is just crazy, right? Yeah, no, they're crazy. It's my favorite group, I'm telling you. They only live for a few hours, and of course you might imagine if you had a few hours to live, what would be your main thing you'd be thinking about? And so they do that. They find a female, they mate, and that's basically their life. So that's interesting. But what does this have to do with the morphological species concept? Well, there's so few traits. In fact, there's no traits that are in common between a male that you see and a female. Now, clearly, the Strepsiptera know who the right species is. Right? They're not fooled. But for us, just looking at them, it's very difficult for us to even match a male with a female. Now, that's a little bit different problem than saying this species of Strepsiptera is different than that species of Strepsiptera. But this is the type of problems you can face when you're relying only on morphology. What if you don't have any characteristics that you can easily latch onto that would help you distinguish, in this case, even males from females? Right? So that's just one example. As an aside, people are relying now on using genetics. So actually, it's cheap enough now just to sequence the organisms that if you really want to match up a male with a female, you look at the genes instead of trying to decipher the morphology. Here's another example that illustrates some of the problems with naming species according to morphology. This is a butterfly that lives in Borneo. Its genus species name is Astrapies fulgurata, and that's what the adults look like. They're kind of pretty butterflies, I suppose. Okay. This is what the larvae look like. So that all the adults are this form. They're monomorphic, one form. When you look at the larvae, people notice that there are many different forms. They're polymorphic, many forms. So all these different forms have names, right?